the story we tell ourselves. There is a story that human beings have been telling themselves for most of recorded history. It goes something like this. We are here, at the center of everything, under skies that were placed there to be looked at and stars that were arranged to be named. The universe, in this story, has a point, and the point is us. It's a reasonable story, if you think about it from the inside. Stand in any field on a clear night and look up. The sky is enormous, and you are standing in it. Not on the edge of it, in it, at the center of the dome of the visible world. Every direction you look, the sky is equally far away. The sun rises for you and sets for you. The moon tracks across the sky in an arc that begins and ends on your horizon. The stars rotate around a fixed point, Polaris, the North Star, as though they are circling the place you are standing. This feeling of centrality is not foolishness. It is a direct consequence of what vision is. Vision is the detection of light that arrives at your location. When you look at the sky, you are always at the center of the sphere of what you can see, because you are always the observer. Pre-Copernican astronomers were not stupid. Many of them were brilliant mathematicians who developed sophisticated models of celestial motion. They just started from the wrong assumption, the assumption that what is true for the eye is also true for the cosmos. That we, being the place where all the light converges, must also be the place where all the universe converges. That assumption is wrong. Not slightly wrong, not metaphorically wrong, but wrong in a way that keeps getting worse the more carefully you look. Wrong about the sun being at the center. Wrong about our solar system being at the center of the galaxy. Wrong about the galaxy being at the center of anything. Wrong about the observable universe being the whole universe. At every step outward, the story of our centrality collapses a little further, and the actual picture comes into view. And that picture is about the true scale of where we are and how large we are relative to everything else that exists. The numbers involved are not just large. They are numbers that the human brain has no real capacity to feel. They can be known intellectually, but they resist being truly absorbed. What we can do is walk through them carefully, from small to large, using comparisons that try to drag the abstract into the concrete. Each step will leave you a little further from the familiar ground of ordinary human experience. By the end, you should feel something, not necessarily dread, though that is one possible response. Maybe awe, maybe a kind of vertigo, maybe a particular quality of silence that comes when you've thought carefully about something very large and found no comfortable place to sit. We'll start where you are. Why our brains fail at this, the scale problem. The human brain evolved over millions of years to solve a specific set of problems. Track animals across a landscape, judge the distance and trajectory of thrown objects, navigate social relationships in groups of 100 or so people, recognize faces, anticipate the behavior of predators, find food and remember where it was. None of those problems required thinking about a billion of anything. The largest meaningful number in the daily life of our ancestors was probably something in the low thousands. The number of people in a large gathering, the number of animals in a herd, the number of days in a long journey. Beyond a few thousand, the brain doesn't generate a real sense of quantity. It generates the concept of many and leaves the precise value to the counting systems it has invented. This is the root of the problem with cosmic scale. When you hear that the observable universe is 93 billion light-years across, you do not feel a quantity. You recognize a number and a unit, but the number is so far outside anything your perceptual system has ever processed that it arrives in your mind essentially as a symbol, a word for something incomprehensibly large, not an actual felt sense of size. The same thing happens with geological time, with national debt, with the number of neurons in your brain. The numbers are technically available but emotionally inert, because the brain has no template for them. This isn't a failure of intelligence, it's a feature of how perception works. When researchers study how people intuitively compare large numbers, they find that the brain switches to a logarithmic scale at high quantities, meaning that most people don't feel much difference between 1,000,000, 1,billion, and 1,000,000,000,000. These are all just a lot. The fact that 1,000,000,000 is 1,000 times larger than 1,000,000 registers intellectually, but not viscerally. There is a demonstration of this that researchers use sometimes. Ask someone to blink once for every $1,000,000 of national debt. Blink for $1,000,000, blink for 1,000,000,000, for 1,000,000,000,000. The blinking rate required to keep up with the difference is physically impossible, and the point lands. These numbers are not just large. They are different in kind from numbers humans have any real experience of. Think of it this way. 1,000,000 seconds is about 11.5 days. 1,billion seconds is about 31.7 years. 1,000,000,000,000 seconds is about 31,700 years, longer than all of recorded human history. The same multiplication that takes days to years to millennia applies across the scales of the universe, except the relevant units are light years, and the multiplications are far more extreme. The human experience of magnitude runs out at around 1,000. Everything above that is abstract. Everything above 1,000,000 is almost indistinguishable in feel. And yet, the universe requires us to work with numbers like a septillion, a 1 followed by 24 zeros, as if they are routine. What we can do, and what good science communication has always tried to do, is find scale models and analogies that bring the numbers into range. These never fully succeed. The universe will remain stubbornly larger than any analogy we build for it. But they can create moments where the scale becomes briefly, partially real, where the abstract loosens and something closer to a genuine understanding lands. The other thing that helps is stepping. Don't try to go from the size of a human directly to the size of the observable universe. Go one scale at a time, allowing each step to settle before taking the next. The disorientation accumulates gradually, and that is the point. By the time you arrive at the outer edge of the observable universe, you should feel a certain quality of vertigo that is the closest the brain can get to genuinely processing the numbers. So let's try to build that feeling, stage by stage, starting with the most modest possible departure from where you're sitting right now. First step: Earth seen from orbit. The International Space Station orbits Earth at an altitude of approximately 420 kilometers. To put that in the terms we use on the ground, 420 kilometers is roughly the road distance from London to Edinburgh, or from Los Angeles to Las Vegas, or from New York City to Boston with room to spare. It's the kind of distance that takes a few hours to drive. A significant trip, but not a transcontinental one. On the ground, it feels substantial. Straight up, 420 kilometers is everything. From the ISS, that distance is what separates the crew from everything that has ever mattered to them. Every person they have ever known, every place they have ever been, every sensation tied to gravity and air and ground. And from that distance, Earth changes character completely. What the crew of the ISS sees through the windows of the cupola module, a dome of glass installed specifically for observation and photography, is the whole planet below them. Not a piece of it, not a region, but the entire curve of it visible in one glance. The atmosphere, which on the ground feels vast and permanent and deep, appears from 420 kilometers as a thin blue line at the edge of the planet, a translucent haze, almost nothing. This view has a name now, the overview effect, coined by the writer Frank White after he spent years interviewing astronauts about what it felt like. The term captures the psychological shift that occurs when you see the Earth as a whole object, from outside, against the black vacuum surrounding it. Astronaut after astronaut has described it using the same words: fragile, small, beautiful, whole. Former NASA astronaut Christina Koch described it as seeing that it's a single planet with a shared atmosphere. The physical reality of that shared atmosphere becomes undeniable when you can see it from outside and watch the curve of it against space. The overview effect is not universal. Not every person who has flown in orbit reports the same intensity of experience. But it is common enough and consistent enough across different cultures and different eras of spaceflight that it tells us something real about the difference between knowing a fact and seeing it. We all know Earth is a sphere. We all know space is dark. But seeing it, looking at the actual planet from outside it in real time with your own eyes, does something that no amount of knowing does. The knowledge becomes real. At 420 kilometers, Earth already looks small. That is the first shock. And 420 kilometers is the closest thing to a baby step that this story has to offer. The Moon. 3 days of silence. The Moon orbits Earth at an average distance of 384,400 kilometers. That number needs to sit for a moment, because the difference between 420 and 384,400 is almost 10,000-fold. If the ISS were a single step outward from Earth, the Moon is 10,000 steps. To travel from Earth to the Moon at the speed of a commercial airliner, which is roughly 900 kilometers per hour, would take about 400 hours or about 17 days. The Apollo astronauts did not travel that slowly. They traveled faster than any humans before them, at velocities around 39,000 kilometers per hour, and it still took 3 days. 3 days of looking at Earth shrinking behind them, becoming a sphere, then a disk, then a bright marble in an absolute black that has no texture, no up, no down. By the time the Apollo 8 crew reached lunar orbit in December 1968, Earth had become small enough to see whole. Astronaut William Anders took a photograph from that orbit that has since been described as one of the most influential photographs ever taken. The Earthrise image, showing Earth as a blue and white sphere rising above the grey lunar horizon against the black of space. It ran on the front pages of newspapers around the world. It is credited by many historians with helping to trigger the environmental movement, because for the first time in history, an image existed that made the Earth's vulnerability visually real rather than conceptually available. You could see, looking at that photograph, that the planet was a finite object, that it had edges, that it was surrounded by nothing. The 12 men who walked on the lunar surface between 1969 and 1972 all reported looking up and seeing Earth. A small, bright dot. A marble. Edgar Mitchell, the 6th person to walk on the Moon, looked up during his walk and saw Earth in the black sky and described an instant of recognition, a feeling that the separation between himself and the universe was something his brain had invented. He later founded an organization dedicated to studying consciousness. He said the experience of seeing Earth from the Moon was the most transformative of his life. The Earth-Moon distance, 384,400 kilometers, is the full width of about 30 Earths placed side by side. 30 Earths, that distance, which took the fastest humans who had ever traveled 3 days to cover, is nothing on the scale of what comes next. The Sun, our closest star, already staggering. The Sun is 149.6 million kilometers from Earth. Light, traveling at 300,000 kilometers per second, takes 8 minutes and 20 seconds to travel that distance. That is fast enough that if you could somehow travel at the speed of light, the absolute speed limit of the universe, you could circle the Earth 7.5 times in a single second. And yet, the Sun is far enough away that even at that speed, the trip takes over 8 minutes. Here is one way to try to feel this distance. If Earth were the size of a grain of sand, roughly 1 millimeter across, the Sun, keeping the same proportional size, would be a sphere about 1.4 meters in diameter. That's about the size of a beach ball or a large exercise ball. And it would be sitting approximately 150 meters away from that grain of sand. Not in the same room, not across a hallway. 150 meters away, which is roughly a city block and a half. Stand next to a grain of sand on a sidewalk and imagine a beach ball sitting somewhere past where you can easily see. That is the Earth-Sun relationship, compressed. At that scale, the Moon would be a sphere about 3 millimeters across, barely larger than the Earth grain of sand, sitting about 40 centimeters from the Earth, and the nearest star to our Sun, Proxima Centauri, would be 40,000 kilometers away. At the grain of sand scale, the nearest neighboring star is farther than the real distance from Earth to the Moon. This is the solar system's fundamental character, mostly empty space. The planets are tiny objects separated by enormous distances, all loosely held together by the gravity of a star that is itself a small object in the context of the galaxy it inhabits. And yet, the Sun, by human standards, is vast. Its diameter is about 1.4 million kilometers. You could fit over 1 million Earths inside it with room to spare. Its mass is large enough that it accounts for about 99.8% of the total mass of the entire solar system. Every planet, moon, asteroid, and comet in the solar system together makes up the remaining 0.2%. Here is what makes this more disorienting. The Sun is ordinary. It is a yellow dwarf star, classification G2V on the stellar catalogue, somewhere in the middle range of stellar sizes and temperatures. It is not among the largest, not among the brightest, not among the hottest. Red dwarf stars, which are smaller, cooler, and dimmer, are actually the most common type in the Milky Way, comprising roughly 70% of all stars. And on the large end, there are giant and hypergiant stars that dwarf the Sun the way the Sun dwarfs Earth. Some of the largest known stars are almost beyond the reach of analogy. Stephenson 2-18, a red hypergiant in the constellation Scutum, has an estimated radius of roughly 2,150 times that of the Sun. If Stephenson 2-18 were placed where our Sun is, it would swallow Mercury, Venus, Earth, Mars, Jupiter, Saturn, and extend well toward the orbit of Uranus. In the grain of sand model, where the Sun is a beach ball 150 meters from Earth, Stephenson 2-18 would be a sphere roughly 3 kilometers in diameter, taller than some mountains. That is a single star. There are hundreds of billions of stars in the Milky Way. Many of them are far larger than the Sun, and every one of them is an ordinary atom of the galaxy, a single point in a disk of stars stretching 100,000 light-years across. The Milky Way, the galaxy we almost can't comprehend. The Milky Way galaxy is approximately 100,000 light-years in diameter. The disk is thought to be about 1,000 light-years thick in most places, with a central bulge that is somewhat thicker. It contains somewhere between 200 and 400 billion stars, depending on how you count the faint ones. It contains a supermassive black hole at its center, Sagittarius, a star with a mass of approximately 4 million times the mass of our Sun. A light-year is 9.46 trillion kilometers. The Milky Way is 100,000 of those. The numbers are genuinely beyond what can be made tactile, but one approach comes close. If the entire solar system, out to the orbit of Neptune, which is roughly 30 times as far from the Sun as Earth is, were shrunk to the size of a grain of sand, the Milky Way would be about 50 kilometers across. The whole solar system, compressed to a point too small to see without a magnifying glass, and the galaxy containing it is still the size of a modest metropolitan area. At that same scale, the nearest star to our Sun, Proxima Centauri, just 4.24 light-years away, would be a few meters from the solar system grain of sand. Stars in our part of the galaxy are roughly that far apart, on average. Trillions of kilometers of empty space between each one. The galaxy, despite containing hundreds of billions of stars, is overwhelmingly, almost entirely empty. Where does our Sun sit within all of this? The Sun is located in a minor spiral feature called the Orion Arm, or sometimes the Orion Spur, located roughly 26,000 light-years from the center of the galaxy. We are not in the galactic center, with its dense star clusters and the gravitational violence near the central black hole. We are not on the outer edge in the sparse halo. We are in the suburbs, a quiet, moderately populated region of one of the minor arms of a barred spiral galaxy. Astronomically speaking, we live in a pleasant but unremarkable neighborhood. The galactic center, 26,000 light-years away in the direction of the constellation Sagittarius, is a place no human instrument has ever seen clearly in optical light because of the dense clouds of gas and dust between us and it. We know it is there from radio observations, from infrared imaging, and from tracking the orbits of stars near the center. Orbits that reveal the gravity of the central black hole in their trajectories as clearly as seeing the drain in a bathtub by watching the water spiral. Stars near the galactic center orbit Sagittarius, a star in timescales of tens of years, at speeds of thousands of kilometers per second, looping around an object they will never directly escape. The Milky Way is our home galaxy. It contains everything in our observable neighborhood that feels, in some sense, close. Every star visible to the naked eye from Earth is in the Milky Way. Every exoplanet ever confirmed to date is in the Milky Way. The nearest other galaxy, the Andromeda Galaxy, is 2.5 million light-years away, about 25 times the full diameter of the Milky Way. The Milky Way is not a small place, and it is one galaxy among an estimated 2 trillion in the observable universe. The local group and what lurks 2.5 million light-years away. The Milky Way is not alone. It belongs to a gravitationally bound collection of galaxies called the local group, a cluster of more than 54 known members spread across a region roughly 10 million light-years in diameter. The two dominant members of the local group are the Milky Way and the Andromeda Galaxy, M31, to use its catalogue designation. Andromeda is the most distant object visible to the naked eye from Earth, appearing as a faint, elongated smudge in the constellation. Andromeda on very clear nights. Its apparent faintness is misleading. It is not a small thing. It is a large spiral galaxy containing perhaps 1 trillion stars, similar in size and structure to the Milky Way. It is faint because it is 2.5 million light-years away. The light you see when you look at Andromeda with your naked eye is 2.5 million years old. It left that galaxy when our ancestors were pre-stone tool hominins, still living in Africa and not yet doing anything that would leave a recognizable archaeological record. By the time that light reached your eye, human civilization had risen, flourished, and produced this video, which you are now watching. Andromeda and the Milky Way are approaching each other. The two galaxies are converging at roughly 110 kilometers per second, fast by any human standard, though modest in comparison to some galaxy merger speeds, and are expected to begin the merger process in approximately 4.5 billion years, with the process taking hundreds of millions of years to complete. The resulting structure will be a different kind of galaxy entirely, likely an elliptical galaxy, with the elegant spiral arms of both predecessors disrupted and scrambled by the forces of the merger. Astronomers have already given this future galaxy a name, Milkomeda, a portmanteau that contains both its parents. Galaxy mergers are not collisions in the everyday sense. Stars within galaxies are separated by distances so enormous relative to the stars themselves that when two galaxies pass through each other, the probability of any two individual stars actually colliding is extremely low. What happens instead is gravitational. Stars are deflected from their orbits, flung into new trajectories, drawn toward the centers of their host galaxies, or expelled into intergalactic space. The shapes of both galaxies deform, extend, and ultimately merge into a new, larger system. It is violent in the sense that enormous quantities of energy are released and the large-scale structure changes dramatically. But it is a gentle violence at the level of individual stars. Beyond Andromeda and the Milky Way, the local group contains a number of smaller dwarf galaxies. From the southern hemisphere, two of them are visible to the naked eye. The large and small Magellanic Clouds, which look like detached pieces of the Milky Way hanging in the southern sky. They are gravitationally associated with the Milky Way and are currently being slowly stripped of material by the Milky Way's tidal forces as they orbit it. The Triangulum Galaxy, M33, is the third largest member of the local group and is only marginally outside naked eye visibility on the best observing nights. The rest of the local group's members are dwarf galaxies, smaller and less luminous, some detected only with telescopes within the last few decades. 10 million light-years of space filled with 54 known galaxies, anchored by two large spirals heading toward each other. The local group is enormous by any human standard, and it is a small cluster in the context of what comes next. The Virgo cluster and the neighborhood beyond. The local group is gravitationally associated with the Virgo cluster, a massive congregation of galaxies approximately 65 million light-years away. The Virgo cluster contains somewhere between 1,300 and 2,000 galaxies, and has a total mass estimated at several million billion solar masses. It is the gravitational core of a much larger structure called the Virgo supercluster, which has been known since the 1950s. The Virgo cluster is not pulling the Milky Way toward it rapidly. The cluster is far enough away that the expansion of the universe counteracts its gravitational pull at our location, meaning the Virgo cluster is not our immediate gravitational destiny. but it is part of the broader structure to which we belong, and understanding how the Milky Way fits into the hierarchy of cosmic structure requires passing through it. What changed our understanding of that hierarchy significantly was the work published in 2014 by astronomer R. Brent Tully and his colleagues at the University of Hawaii. Tully's team had been building a catalogue of the peculiar velocities of galaxies, the motions of galaxies that are attributable to gravity rather than to the general expansion of the universe. If you subtract out the expansion, what remains is the gravitational motion. Galaxies flowing toward concentrations of mass like water flowing toward a drain. By mapping these flows across an enormous volume of space, they found that the Milky Way, the local group, the Virgo cluster, and roughly 100,000 other large galaxies are all part of a single gravitational basin. They flow together, converging toward the same gravitational center. Tully's team defined that entire basin as a supercluster and named it Laniakea, from the Hawaiian words Lani, meaning heaven, and Akea, meaning spacious or immeasurable. The name honors the Polynesian navigators who crossed vast stretches of the Pacific using only stars and currents and intimate knowledge of the sea, mapping their position in a world far larger than any single island. There is something appropriate about naming our cosmic home after people who understood how to navigate immensity. Laniakea stretches approximately 500 million light-years across. It contains a combined mass roughly equivalent to 100 million billion times the mass of our Sun. Its 100,000 member galaxies are threaded through a structure of filaments and voids, all flowing in the same general direction toward the gravitational heart of the supercluster, a region called the Great Attractor. The Great Attractor is located about 160 million light-years from the Milky Way, in the direction of the constellation Centaurus. It is not a single object, but a dense concentration of galaxy clusters. The Norma, Centaurus, and Hydra clusters, among others, whose combined gravity creates a gravitational well that influences the motion of everything within Laniakea. We are being pulled toward it. The Milky Way is moving at several hundred kilometers per second, relative to the cosmic background, and a significant portion of that motion is directed toward the Great Attractor. We are falling, in the slow gravitational sense, toward a mass concentration we will never reach before the accelerating expansion of the universe carries everything too far apart for gravity to matter. Where does the Milky Way sit within Laniakea? Not at the center. Near the outer edge, close to the boundary with a neighboring supercluster complex called Perseus Pisces. If Laniakea were a country, we would be in a village near the border, far from the capital. And even Laniakea is not the final layer of structure. There is evidence that it is itself embedded in a larger structure. The Pisces Cetus supercluster complex, a filament of the cosmic web extending more than 1 billion light-years. The context keeps expanding. Each time astronomers have thought they had found the largest coherent structure, another layer has emerged. The cosmic web, the universe's skeleton. Pull back to a scale where even superclusters are small features, and something remarkable comes into view. The universe is not a uniform soup of matter. It is not even a random distribution of galaxies. It has structure that repeats at every scale from clusters to superclusters and beyond. And that structure looks like something biological. The large-scale arrangement of matter in the universe is called the cosmic web. It consists of dense filaments of matter, dark matter and ordinary matter together, stretching for hundreds of millions or billions of light-years, with galaxy clusters and superclusters clustered at the nodes where filaments intersect. and vast, nearly empty regions called voids, filling the spaces between. The filaments themselves are long, thin concentrations of matter strung between gravitational nodes. Galaxies accumulate along them, distributed something like beads on a string or dew on a spider's web. The intersections, where multiple filaments meet, are where the most massive structures form. The great galaxy clusters with their thousands of member galaxies, their hot intracluster gas glowing in X-rays, their gravitational wells deep enough to bend light visibly. Between the filaments are the voids, the great empty bubbles of the cosmic web. These are not truly empty. They contain some diffuse matter, some isolated galaxy groups, and a faint background of dark matter. But they are dramatically underdense compared to the filaments, and their boundaries mark the transition between the rich, connected structure of the web and the sparse, disconnected hinterlands. Some voids are hundreds of millions of light years across. If you lived in a galaxy deep inside a void, you might look out and see almost nothing. The nearest large galaxy clusters could be hundreds of millions of light years away. The cosmic web that is so visually striking from our observational vantage point would be all but invisible from deep inside a void, because there would be almost nothing to trace its outlines. The Milky Way sits near the local void, an underdense region that stretches for hundreds of millions of light years roughly in the direction away from the Virgo cluster. We are on the edge of a void, at the boundary where sparse emptiness meets the slightly denser structure of the filaments leading toward the Virgo cluster and beyond that toward the Great Attractor. The cosmic web did not have a designer. It grew from the seeds of quantum fluctuations, tiny, random variations in the density of matter that existed in the first moments after the Big Bang. Those variations were incredibly small, density differences of just 1 part in 100,000. Over 13.8 billion years, gravity amplified those tiny variations. Regions that were slightly denser than average attracted more matter, which made them denser still, which made them attract even more. Regions that were slightly less dense lost matter to their neighbors and became increasingly empty. The small became smaller, the dense became denser. The web grew from almost nothing into the vast structure we can now observe and map. Everything that exists, every galaxy, every star, every planet, every living thing, is a consequence of those tiny quantum fluctuations in the first fractions of a second. The observable universe, the limit of the light. Now we reach the outer boundary of what can be seen. And immediately we encounter one of the most disorienting facts in all of cosmology. The observable universe is the region of space from which light has had time to reach us since the Big Bang. Since the Big Bang happened approximately 13.8 billion years ago, and since light cannot travel faster than 300,000 kilometers per second, you might expect the observable universe to extend 13.8 billion light years in every direction. It does not. It extends approximately 46 billion light years in every direction, giving the observable universe a total diameter of about 93 billion light years. The reason for this paradox, a universe that appears to be nearly 3.5 times older than it is large, measured in light years, is cosmic expansion. Space itself has been expanding since the Big Bang, and this expansion carries matter with it. The galaxies whose light we are now receiving were much closer to us when they emitted that light than they are today. In the time it took that light to travel to us, the universe expanded, carrying those galaxies much farther away. The light we now see from the most distant objects in the universe was emitted when those objects were perhaps 1 billion light years away. Those same objects are now located roughly 46 billion light years from us. because the intervening space has stretched. This expansion is happening everywhere simultaneously. There is no center from which it expands. Every point in the universe is, from its own perspective, at the center of the expansion. Every other point appears to be moving away from it. This is the nature of the Big Bang. Not an explosion in space, but an expansion of space itself, like the surface of a balloon being inflated. Any 2 points on the balloon move apart as it inflates, not because they are moving through the rubber, but because the rubber between them is growing. The observable universe contains an estimated 2 trillion galaxies. That number, 2 trillion, was revised upward by astronomers in 2016 from a previous estimate of about 200 billion, based on a more careful analysis of Hubble Deep Field observations combined with modeling of galaxies too faint to detect directly. 2 trillion galaxies, each of them a system of stars and gas and dark matter, each with its own history spanning billions of years, each with planets orbiting most of its stars, each too distant for us to visit, and most too distant for us to see in any detail. The number of stars in the observable universe is estimated at roughly a septillion, a 1 followed by 24 zeros. For comparison, there are approximately 7.5 quintillion grains of sand on all of Earth's beaches. That's a 1 followed by 18 zeros. There are about a million by 18 zeros. There are about 1 million times more stars in the observable universe than grains of sand on every beach on Earth, and most of those stars have planets. The number of planets in the observable universe is probably larger than the number of stars, because most stars have more than one. There is a demonstration of this depth that more than any number conveys what we are actually talking about. In 1995, astronomers pointed the Hubble Space Telescope at a patch of sky in the constellation Ursa Major, a patch so small it would be covered by a grain of sand held at arm's length from your eye. They let the telescope stare at that patch for 10 consecutive days, collecting photons that would otherwise be invisible. What they found in that tiny sliver was approximately 3,000 galaxies, not stars. Galaxies, each one a system of hundreds of millions to hundreds of billions of stars. The Hubble Extreme Deep Field, compiled in 2012 from even longer exposures, revealed about 5,500 galaxies in a similarly minuscule patch of sky. And every direction you point a telescope, you find the same thing. Galaxies at every depth, from the relatively nearby to the nearly 13 billion light-years away, stacked behind each other like audience members in a stadium extending all the way to the horizon. The sky is effectively tiled with galaxies in all directions, visible in any direction if you look deeply enough. There are about 41,000 square degrees in the total sphere of the sky. Extrapolate across all of them, accounting for the billions of galaxies too faint to detect even with the best instruments we currently have, and you arrive at that estimate of 2 trillion. 2 trillion galaxies. In the region of the universe we happen to be able to observe from our particular location right now. Within this observable universe, the Milky Way is one of 2 trillion. It is, by the measure of its stellar mass, somewhere in the mid-range. Not the smallest galaxy by far, but not the largest. In the vast ensemble of galaxies, the Milky Way is ordinary. Beyond the horizon, what we cannot see. The edge of the observable universe is not the edge of the universe. It is, precisely, the edge of what we can observe. Beyond the particle horizon, the spherical boundary at 46 billion light-years in every direction, the universe almost certainly continues. Light from those regions has not had time to reach us, or was emitted at a time when the universe was still opaque to radiation and could not travel freely. There is nothing physically different about space at that boundary. It is a horizon imposed by the finite speed of light and the finite age of the universe, not a wall or an edge of anything. If someone were living in a galaxy currently 100 billion light-years from Earth, they would observe their own observable universe centered on their location. They would see galaxies we cannot see because their particle horizon extends to regions from which light can reach them, but not us. Our two observable universes would overlap in the middle. There would be a region that both of us can see, but each of us would have access to regions invisible to the other. We would look like a pinpoint of light to them, probably too faint and too redshifted to detect with any instrument they currently possess. How large is the total universe beyond the observable portion? We do not know. The honest answer is that we may never know. Based on measurements of the large-scale geometry of space, which appears to be flat, in the sense that parallel lines in large triangles remain parallel rather than curving together or apart. The total universe appears to be at least 250 times the diameter of the observable portion. Some estimates, based on different interpretations of the same data, are much larger. Some models of cosmic inflation, the rapid expansion thought to have occurred in the first fractions of a second after the Big Bang, suggest that the total universe could be many orders of magnitude larger than what we can observe. Possibly infinitely large. Inflation, if it occurred, and there is strong observational support for some version of it, would have taken a tiny patch of space and expanded it at speeds enormously faster than the speed of light, in a fraction of a second, producing a universe so large that our entire observable universe is a negligibly small region within it. The edge of what we can observe would be an arbitrary boundary within an essentially infinite space, not a meaningful limit of anything except our vision. The implication is genuinely staggering. The 93 billion light-year wide sphere we call the observable universe, containing its 2 trillion galaxies and its septillion stars, might be an almost immeasurably small fraction of the total. The visible universe might be to the total universe what a single grain of sand is to all the beaches of Earth, or smaller. We genuinely do not know. The cosmic calendar, our position in time. Everything so far has been about space, but there is another dimension of the comparison between us and the universe, and it is no less vertiginous. Time. The universe is approximately 13.8 billion years old. Human beings have been farming for roughly 12,000 years. Writing has existed for about 5,000 years. The Industrial Revolution is barely 250 years old. Modern physics, which gave us the tools to understand the scale of the universe at all, is roughly 150 years old. We are new here, extraordinarily, almost absurdly new. Carl Sagan popularized a way of feeling this that he called the cosmic calendar, compressed the entire 13.8 billion year history of the universe into a single calendar year, midnight on January 1st to midnight on December 31st. At that scale, each month represents just over 1.1 billion years. Each day represents about 37.8 million years. Each hour represents about 1.57 million years. Each second represents about 438 years. In this compressed year, the Big Bang happens at midnight on January 1st. January 1st through much of February is occupied by the formation of the first stars and galaxies, a process that took hundreds of millions of years. Our Milky Way, our home galaxy, formed in approximately cosmic May, around 4 billion years after the Big Bang. Our Sun and the Solar System did not form until cosmic September, roughly September 2nd, approximately 4.6 billion years ago. Earth, forming alongside the Sun from the same collapsing cloud of gas and dust, also appeared in September. The first life on Earth, simple single-celled organisms, probably existing as chemical systems before that, appears around late September or early October on this calendar. For the next 2 months of the cosmic year, life remains simple and single-celled, evolving slowly, developing photosynthesis in cosmic October, producing the oxygen that would eventually transform the atmosphere. The first complex multicellular animals don't appear until early December. Fish evolved around December 19th. Land plants appeared around December 20th. Dinosaurs appeared on December 25th, Christmas Day, and went extinct on December 30th at the end of the Cretaceous mass extinction. The entire Cretaceous period, from the first dinosaurs to their extinction, spans roughly December 25th to December 30th. Early humans, the first anatomically modern Homo sapiens, appear around 11:52 p.m. on December 31st. That is 8 minutes before midnight on the last day of the year. We began farming at approximately 11:59 and 32 seconds. The Great Pyramid of Giza was built at 11:59 and 51 seconds. The Roman Empire rose and fell within the last few seconds. Columbus reached the Americas at roughly 11:59 and 58 seconds. The entire history of modern science, from Galileo to the James Webb Space Telescope, happened in the final 2 seconds of the cosmic year. All of recorded human history, every battle, every empire, every philosophy, every work of art, every technological revolution from fire to the microprocessor. The last 10 seconds of December 31st. Every person whose name you recognize, every historical figure you have ever studied or admired, lived in those last 10 seconds. And a single human life, 80 years, represents about 0.18 cosmic seconds. Your entire life, at the scale of the universe, is a blink that occurs near the end of the very last moment of a year that contains almost everything. The history of being moved. Aside. None of this knowledge is natural or intuitive. It had to be fought for, step by step, against the persistent human conviction that we are at the center of things. The Ptolemaic model of the cosmos, which placed Earth at the center of a system of concentric spheres carrying the Sun, Moon, planets, and stars, was not merely accepted, it was mathematically sophisticated, observationally grounded, and philosophically elaborated over centuries. It matched the data available before the telescope. The planets did appear to move in the sky in ways that required explanation, and Ptolemy's model, with its epicycles and deference, actually predicted those positions with reasonable accuracy for its time. Nicholas Copernicus published his heliocentric model in 1543, moving the Sun to the center of the solar system and placing Earth among the planets. This was not immediately controversial in the way the popular story sometimes suggests. The controversy built slowly, and the full confrontation with the Church came with Galileo, decades later. But the shift was philosophically profound. Copernicus was not just changing the geometry of the solar system, he was removing Earth from the special position. Galileo's telescopic observations in the early 17th century provided concrete evidence. Mountains on the Moon, moons orbiting Jupiter, phases of Venus consistent with it orbiting the Sun rather than the Earth. Each observation made the Ptolemaic picture more difficult to maintain. Johannes Kepler, working with Tycho Brahe's precise measurements of planetary positions, showed that the planets moved in ellipses, not circles, a discovery that removed the last purely aesthetic argument for geocentrism, the idea that perfect circular motion befitted the heavens. By the early 18th century, heliocentric solar system models were accepted by virtually all working astronomers. But the solar system remained, in most minds, the extent of the universe. The stars were fixed points on a distant sphere, their distances unknown, their nature uncertain. Whether they were other suns, whether there were other solar systems, whether the Milky Way was just part of something larger, these questions were not answerable until much later. William Herschel, in the late 18th and early 19th centuries, made the first serious attempt to map the Milky Way by counting stars in different directions. His map placed the Sun near the center of the galaxy. Wrong, but a genuine attempt at a scientific answer. The idea that the Milky Way had a structure at all, that it was a disk of stars rather than a random distribution, was itself a step forward. Harlow Shapley corrected Herschel's error in the early 20th century by studying the distribution of globular clusters, dense balls of hundreds of thousands of stars that orbit the galactic center. He found that they were concentrated in the direction of Sagittarius, not uniformly distributed around us, indicating that the galactic center was far off in that direction and that we were somewhere in the outer disk. Then, Edwin Hubble, in the 1920s, resolved the long-running debate over whether the nebulae, which are visible as cloudy patches of light spread across the sky, were nearby gas clouds in the Milky Way or distant systems of stars comparable to the Milky Way itself. Using a class of variable stars called Cepheids, which pulsate with a period directly related to their luminosity, Hubble measured the distances to several nebulae and found them to be millions of light-years away. The Andromeda Nebula was a galaxy in its own right, containing millions of stars, as large and complex as the Milky Way. The universe had just become vastly larger than anyone had understood. And then Hubble made the discovery that changed cosmology more profoundly than anything before it. The galaxies were moving away from us. Almost all of them, in almost every direction, showed red-shifted light that had been stretched to longer, redder wavelengths by the recession of the source. The farther a galaxy was, the faster it was moving away. The universe was expanding. This meant that in the past, everything was closer together. It meant that if you ran the expansion backward, there was a moment when everything was compressed into a very small, very hot, very dense state. This was the observational foundation of the Big Bang Theory. The universe had a beginning. It had been 13.8 billion years since that beginning. And in that time, it had expanded to a scale that defied any intuitive framework we had built for understanding our place in it. Each of these discoveries was a further removal from centrality. Copernicus moved Earth from the center of the solar system. Shapley moved the Sun from the center of the galaxy. Hubble showed the galaxy was one of many. The expanding universe showed that there was no center at all, or rather, that every point was equally central. The universe is not arranged around us. We are one configuration of matter among an incomprehensible number of configurations. In one galaxy among trillions. In one moment of a 13.8 billion year history that will continue for incomprehensibly longer. What our smallness actually implies. So what follows from all of this? What does it mean to be the size and age that we are, in the place that we occupy? The most direct implication is the one that feels most uncomfortable. The universe did not make room for us. It was not built around us. It is not aware of us. The 93 billion light-years of the observable universe existed long before we appeared, and the vast majority of it has no relationship to us whatsoever. No causal connection, no influence in either direction, nothing that could be described as caring or noticing or planning. Most of the universe's 13.8 billion year history occurred before there were any creatures to experience it. The first 9 billion years produced stars and galaxies and heavy elements without a single conscious observer anywhere we know of. This indifference is not hostile. Indifference requires no attention at all, which is precisely the point. The universe is not cold toward us. It has no warmth or coldness as orientations toward anything. The galaxy cluster Abel, 2029, more than 1 billion light-years away, contains more mass than can easily be conceived. Not one particle in it is in any way affected by whether humans live or die, flourish or destroy themselves. The universe's indifference is so complete that calling it indifference is almost an anthropomorphism. It implies the possibility of the opposite, of care, where no such possibility exists. The disturbing implication of our size is not just that we are small. It's what smallness implies in a universe with no apparent center, no evident purpose, and no mechanism by which a pale blue dot at the edge of a supercluster could have any cosmic significance. The universe will continue long after every trace of our civilization is gone. The sun will expand into a red giant in about 5 billion years, engulfing or sterilizing Earth in the process. Long before that, within 1 billion years, on current estimates, the increasing luminosity of the sun will make Earth's surface too hot for liquid water oceans, ending the conditions that complex life currently requires. The stars will burn out over trillions of years. Even the long-lived red dwarfs, which burn so slowly they can persist for tens of trillions of years, will eventually exhaust their fuel and fade. The black holes will eventually evaporate through Hawking radiation over timescales so long that they make the current age of the universe look like a preliminary sketch. A stellar mass black hole would take roughly 10 to the power of 67 years to evaporate, and a supermassive black hole would take 10 to the power of 100 years or more. And then, the universe will be cold and dark and essentially empty, and it will remain that way for longer than it has already existed. Far, far longer. Our entire civilization, everything we have built and thought and felt and argued about, will leave no trace on that timeline. The universe will not remember us. There will be nothing left to do the remembering. There is a particular quality to this thought that philosophers have returned to repeatedly across different eras. The philosopher Blaise Pascal, writing in the 17th century, when the shift from the Ptolemaic to the Copernican picture was still relatively fresh, captured the feeling with unusual precision. He wrote that the eternal silence of infinite spaces filled him with fear. Note the word silence, not hostility, not the terror of something threatening, the terror of nothing responding, of crying out into a universe that has no mechanism for hearing. That particular fear, the fear of the absolute absence of response, is older than Pascal, but he articulated it in a way that still resonates. The universe is not menacing. It is simply not listening. And for a species whose entire existence is organized around communication and meaning and the expectation of response, that absence is genuinely disturbing. The physicist Richard Feynman framed it differently, with his characteristic directness. The universe doesn't know we're here, he observed. And if it doesn't know we're here, then we have to decide for ourselves what our being here means. The scale of the universe does not answer the question of meaning. It simply removes the answer most people assumed without thinking about it. The answer that says the universe was arranged around us, and therefore we matter by cosmic decree. The cosmic decree turns out not to exist. The decree, if there is one, has to come from within. And there is another disturbing implication that follows from the scale of the universe in a different direction. If the universe contains 2 trillion galaxies, each with hundreds of billions of stars, and most of those stars have planets, and life has arisen at least once, then what about all the rest? The mathematics of the situation would seem to overwhelmingly favor the existence of other life in the universe. Not necessarily intelligence, not necessarily anything recognizable, but some kind of chemistry that crosses from non-living to self-replicating, some kind of process that makes copies of itself, that evolves, that adapts. And yet, we see nothing. We hear nothing. No signal, no trace, no contact. The universe is vast and old and apparently capable of producing life. And from our tiny vantage point, it is completely silent. This is the Fermi paradox, named after the physicist Enrico Fermi, who is said to have asked over lunch in 1950 simply, "Where is everybody?" The silence has possible explanations. Maybe intelligent life is genuinely rare. Maybe the emergence of complex multicellular life, or of brains capable of abstract reasoning, or of technological civilization requires a series of improbable steps, each of which filters out most candidates. Maybe intelligent life regularly develops and then destroys itself before it can communicate across interstellar distances. A possibility that, for an intelligent species with nuclear weapons and the capacity to reshape its own climate, carries a special and uncomfortable resonance. Maybe it communicates in ways we don't recognize, or at frequencies we haven't listened to, or has no reason to announce itself to unverified strangers across the void. Maybe the universe's timescales are long enough that intelligence arises in sequence, rather than simultaneously across the cosmos. And we are simply among the earliest, finding ourselves in an era of cosmic youth before the galaxy fills with minds. Or maybe something about the nature of the universe makes sustained intelligent civilization genuinely fragile. A possibility that has been called the Great Filter, the idea that somewhere in the progression from simple chemistry to complex spacefaring civilization, there is a step that almost nothing successfully crosses. If that filter lies behind us, we are extraordinarily lucky survivors. If it lies ahead of us, the silence of the cosmos may be telling us something about our own future that we would rather not hear. None of these explanations is entirely satisfying. Each of them, taken seriously, has disturbing implications of its own. If we are rare, then the universe is even emptier of meaning than it appears. If intelligent life regularly destroys itself, we have reason to examine our own trajectory with unusual urgency. If the great filter is ahead of us, our present moment takes on a particular weight. If intelligence is sequential and we are early, we are alone for a span of cosmic time that makes all of human history look like a breath. The scale of the universe does not resolve the Fermi paradox. It makes it more pressing. The other side. Awareness in an unaware universe. Here is where the picture changes, or rather, where a second picture emerges alongside the first one, without cancelling it. The universe is 93 billion light-years across. It contains 2 trillion galaxies. It has been expanding for 13.8 billion years. It will continue for trillions more. It is almost entirely dead matter and energy, plasma, dark matter, radiation, gas, rocks orbiting stars, stars burning fuel. Black holes accreting matter, empty space stretching between structures that have no awareness of each other. Two filaments of the cosmic web, each spanning hundreds of millions of light years, can pass within relatively close proximity, in cosmic terms, and neither of them knows it. The galaxy clusters at their intersection points, each containing thousands of galaxies, exist in perfect mutual ignorance. The universe processes energy according to the laws of physics, without any of it meaning anything to any of the structures involved. And on one particular rocky planet, around one particular ordinary star, in one particular quiet suburb of one particular galaxy, in one particular supercluster, something happened that, as far as we know, is unique in the observable universe. Matter became aware of itself. This is not a small thing to say. Awareness, consciousness, is the capacity to have subjective experiences, to know that there is something it is like to be you, to look at the world and have the world mean something. We do not know precisely how this emerged from chemistry and physics. It remains the deepest unsolved problem in science, the question of why certain arrangements of matter give rise to inner experience at all, rather than simply processing information in the dark. But whatever the mechanism, it happened. The atoms that make up your brain are the same atoms that make up the rocks and the stars and the interstellar gas clouds. Iron, carbon, oxygen, hydrogen, the same elements, manufactured in stellar interiors over billions of years and scattered through supernova explosions before being gathered into a solar system, a planet, and eventually the biology that uses them now. The atoms themselves are not different. What is different is how they are arranged, the pattern, the organization, the extraordinary complexity of information processing that constitutes a nervous system. The astronomer and science communicator Carl Sagan captured this with a phrase that has been widely quoted precisely because it is accurate and not merely poetic. We are made of star stuff. The carbon in your body was forged in the core of a star that died before the sun was born. The iron in your blood was produced in the last moments of a massive stellar death, a supernova explosion that scattered its contents across the galaxy. You are, in a genuinely literal sense, made of material that has been through the interior of at least one star and probably more. You are the cosmos reconfigured into a pattern that can look back at the cosmos and say, I recognize where I came from. The universe spent 13.8 billion years arranging matter into increasingly complex configurations. Quarks into protons and neutrons into atomic nuclei and electrons into atoms into molecules into organic chemistry into self-replicating structures into cells into organisms into ecosystems into the evolutionary system that eventually, on this particular planet, produced creatures who could look up at the sky and calculate the rate at which the universe is expanding. Who could reconstruct the first moments after the Big Bang from faint echoes still detectable in the microwave background radiation? Who could determine the composition of stars thousands of light years away from the way their light spreads into a spectrum? Who could build a machine the size of a city bus, park it 1 million miles from Earth in the cold dark between the planets, and use it to take photographs of galaxies from the first few 100 million years of cosmic time? You can know those things. The universe, insofar as anyone can tell, cannot. In a cosmos that is almost entirely unconscious matter, the emergence of awareness, the fact that the universe has produced, at least once, something capable of knowing that it exists, is genuinely remarkable. Carl Sagan framed it this way: we are a way for the cosmos to know itself. He wasn't speaking metaphorically about human specialness in some cosmic ranking system. He was making a factual observation. Knowledge of the universe does not exist in the universe unless something capable of knowledge exists in the universe. We are that something. We are, as far as we know, the universe's capacity for self-reflection. And self-reflection requires no external validation to be real. There is something in this that runs deeper than comfort or consolation. It isn't that we are important because we are conscious, or that consciousness is cosmically significant in a way that should make us feel better about our size. It is something stranger. The universe does not benefit from our awareness of it. It is not incomplete without observers. But the existence of observers changes something about what the universe is, not its physics, not its scale, but whether the facts about it are facts for anyone. A universe in which no conscious creature ever existed would have had the same history, the same physics, the same large-scale structure. The only thing it would not have had is knowledge of any of that. Knowledge requires a knower. The knower, in this case, is us. And perhaps others we haven't found yet, living in the silence between the stars. The astronauts who experience the overview effect are doing something structurally similar at a much smaller scale. They are looking at the whole Earth from outside it and having the experience of seeing it as a system, a real, physical, fragile, finite system, rather than as the background against which life is lived. The shift is not in the facts, which were already known. It is in the feel of the facts, which becomes suddenly and viscerally real when you can see the whole thing at once. Every astronaut who has described that experience has said that it changed something. Not what they knew, but how they held what they knew. The knowledge that the atmosphere is thin became real, in a way that reading about it had never achieved. What the scale of the universe invites, not requires, but invites, is something like that same shift at a larger level. Not despair, because despair requires a situation in which something that should have been better has gone wrong. The universe has not failed us. We have simply discovered its actual dimensions, and they are very different from what we assumed. And not insignificance, because insignificance is a comparison within a ranking system, and the universe has no ranking system that places consciousness anywhere in particular. What the scale of the universe offers, if you are willing to take it, is the particular quality of humility that comes from having genuinely confronted a larger reality than you expected. The recognition that the frame within which we make our decisions, our conflicts, our definitions of importance, is a genuinely small frame inside a genuinely vast and ancient and largely indifferent cosmos. And that despite all of that, here we are, aware, looking. What new telescopes are adding? The story of our size in the universe is not complete. It is an ongoing scientific project, and the most recent tools available to astronomers are adding new chapters at a pace that would have seemed extraordinary even a decade ago. The James Webb Space Telescope, launched in December 2021 and fully operational since 2022, is the most powerful space observatory ever built. It observes primarily in infrared light, which allows it to see through dust clouds that block optical telescopes and, crucially, to detect the highly redshifted light of extremely distant galaxies, galaxies from the first few 100 million years of the universe's history, when the cosmos was still young enough that many structures we now take for granted had not yet formed. Its mirror, at 6.5 meters across, collects more than 6 times the light-gathering area of the Hubble Space Telescope. It sits 1 million miles from Earth at a point called L2, a gravitational equilibrium position where the combined pull of Earth and Sun allows it to stay in a fixed orientation relative to both, shielded by a sun shield the size of a tennis court that keeps its instruments at the cryogenic temperatures required for infrared sensitivity. Its early observations produced immediate surprises. Among the most discussed are a set of galaxies detected from the universe's first 500 to 700 million years. Galaxies that are substantially more massive, and in some cases more structurally developed, than the standard models of galaxy formation predicted for that early epoch. When these results were published, they generated significant discussion and some shock among cosmologists. One researcher, Erica Nelson, at the University of Colorado, described her reaction to one set of results simply: "It is bananas." She meant it technically. The galaxies appeared to have assembled their stellar mass far faster than the dominant theoretical framework easily accounts for. These results do not overturn the Big Bang. They do not suggest the universe is a different age or size than we thought. What they suggest is that the early universe was more efficient at forming large structures than our models predicted. That something in the physics of galaxy formation in the first billion years needs refinement. Whether that refinement will be minor adjustments to the timing of known processes or something more fundamental is an active area of research. The James Webb Space Telescope has essentially opened a new window onto an era of cosmic history that was previously nearly inaccessible, and the view through that window is already telling us things that revise our understanding of how we got here. Webb is also, for the first time, allowing astronomers to analyze the atmospheric chemistry of planets orbiting other stars, exoplanets, in real detail. When a planet passes in front of its star, a small fraction of the star's light filters through the planet's atmosphere before reaching our telescopes. The way different wavelengths of that light are absorbed or transmitted reveals the molecules present in the atmosphere: water vapor, carbon dioxide, methane, sulfur dioxide, and potentially others. This is genuinely new science. 50 years ago, the existence of exoplanets was theoretical. 30 years ago, we had confirmed a handful. Today, we have confirmed more than 5,000, and the James Webb Space Telescope is beginning to tell us what their air is made of. But there is something deeper about our size in the universe that even the most powerful telescope cannot resolve, because it concerns not what we can see but what we are made of. And here the picture becomes more disorienting still. Ordinary matter, the stuff that makes up stars, planets, gas clouds, people, and everything astronomers have been studying for their entire professional lives, accounts for approximately 5% of the total energy content of the universe. 5%. The rest consists of two things we cannot directly detect and do not understand: dark matter and dark energy. Dark matter makes up roughly 27% of the universe's total energy content. It does not emit, absorb, or reflect light, hence the name. It interacts with ordinary matter only through gravity. We know it exists because galaxies rotate in ways that cannot be explained by the mass of their visible stars alone. The outer regions of spiral galaxies rotate too fast, implying they are embedded in halos of additional mass that we cannot see. We know it exists because clusters of galaxies bend light from more distant objects far more than their visible mass would allow. We know it exists from detailed maps of the cosmic microwave background, the faint afterglow of the Big Bang, which would have a different pattern of temperature fluctuations if dark matter were absent. What dark matter actually is, what particle or field constitutes it, remains one of the deepest unresolved questions in physics. decades of experiments, from underground detectors to collider searches, have not identified it. Dark energy makes up the remaining 68%, the dominant component of the universe's total content. It is the name given to whatever is causing the expansion of the universe to accelerate. For most of the universe's history, it was assumed that gravity would gradually slow the expansion, that the mass of the universe would, over billions of years, eventually bring the expansion to a halt and possibly reverse it. In 1998, two independent teams studying distant supernovae found the opposite. The expansion is speeding up. The universe is not decelerating under its own gravity. It is expanding faster with time, driven by something with negative pressure that acts against gravity on the largest scales. That something is dark energy. Its nature is entirely unknown. The best theoretical candidate, a constant energy density associated with the vacuum of space, matches observations reasonably well, but cannot be calculated from first principles without producing an answer that is wildly wrong. Put this together: 68% dark energy, unknown nature; 27% dark matter, unknown nature; 5% ordinary matter, which is everything we have ever seen, touched, built, or studied. We are made of the minority constituent of the universe. The universe is mostly made of things that are invisible to us, that pass through us without interaction, that we can detect only by their gravitational effects and their influence on the large-scale structure of space. In every kilogram of air you breathe, every glass of water you drink, every star you observe through any telescope, all of it together is a 5% fraction of the total inventory. The universe has an enormous majority constituency that remains, despite decades of effort, almost completely mysterious. This means the story of our size is, in one sense, even more extreme than it first appears. We are not just small spatially and temporally, we are made of the rarest ingredient. The universe is predominantly composed of things we cannot directly perceive, cannot yet characterize, and are only beginning to map through their effects on the 5% we can see. The quiet fact and what to do with it. In 1990, as Voyager 1 was completing its primary mission and heading into the outer solar system, Carl Sagan persuaded NASA to do something unusual. He had been arguing for the idea for years. That before the spacecraft's camera was shut down permanently to conserve power, it should be turned around, one final time, to look back at the inner solar system from where it now was. NASA eventually agreed. On February 14, 1990, from a distance of about 6 billion kilometers from Earth, roughly 40 times the distance from Earth to the Sun, Voyager 1 executed the maneuver and took a series of photographs. The images were assembled into a mosaic of the solar system as seen from outside it. In one of those frames, Earth appears. It is a tiny point of light, less than a pixel in size. It sits in a stripe of scattered light, sunlight caught in the camera's optics, a rainbow of artifact, a smear of camera flare that happens to pass through the frame where Earth sits. Earth, in that image, is what Sagan called a pale blue dot. Not because it is blue in the way the famous photographs from the moon show it. This image was taken from much farther away with a wide-angle lens that made all the inner planets tiny. Earth is pale and faint and fractional, a mote of dust suspended in a sunbeam. Sagan wrote about that image in 1994, in a book he titled after it, and what he wrote has been read by more people since than perhaps anything else he produced. He pointed out what the image implies, that everything that has ever happened to any human being, everything any human being has ever done, happened on that pale dot. Every act of courage and cruelty, every civilization, every species extinction, every work of art, every scientific discovery, every child born and every person who died, all of it happened on a fraction of a pixel, floating in a vast and largely empty solar system, which is itself a tiny system in the outer suburbs of one galaxy among 2 trillion. That particular photograph, technically mediocre, scientifically routine, just one more image from a spacecraft that had already produced thousands of scientific results, has become one of the most widely reproduced images in the history of science. It takes the abstract fact that Earth is small and makes it visible. You look at it and the fact lands differently, not louder, necessarily, not more informative than the numbers alone, but real in a way that numbers resist being. The dot is there. You can see it. That is the planet. That is all of it. We are on that dot. We are a footnote in a document no one is reading. And yet, the document exists. We are small. We are recent. We are made of 5% of the universe's total inventory. On one planet around one ordinary star, at the edge of one supercluster, in what may be an almost negligibly small fraction of the total universe. And we are the only part of this enormous, ancient, indifferent universe that knows any of that. So far. If you've made it this far, you're already the kind of person who doesn't look away from the uncomfortable questions, the ones that leave you sitting quietly afterward, the ones that make the ordinary business of life feel briefly translucent. This channel exists for exactly that kind of curiosity. If this is the conversation you want to be in, subscribe and stay with us, because the universe still has more to show us, and we're not finished looking.